Okay, good morning everyone. Today our group is excited to present our project Automate Activity-Based Tower Simulation Framework for Bangkok using MATSIM. This project is supervised by Associate Professor Virat Mungsin, and there are our team members Valanthorn Chantawong, Project Coordinator and Pipeline Lead, Imdet Janjaran Integration and GUI Lead, Natakit Kirarachanon Testing and Documentation Lead, and Paripong Nanasang, Simulation Lead. Let's start with a quick overview of our project. Our program takes input data from activity theme, include synthetic population, activity schedule, and tip table. Then the data is converted and used in MATSIM to simulate agent tower behavior. And finally, the simulation results are visualizing using SimWrapper. The main problem we address is that setting up MATSIM manually is complex, time-consuming, and difficult to scale across Bangkok. Each area often requires repeat configuration, which makes the workflow inefficient and hard for non-expert users. Another key challenge is data integration. Activity Sim and MATSIM use different data formats, so converting data between them usually requires manual processing and can easily cause error. Therefore, our objective is to develop an automated simulation pipeline for Bangkok. User only needs to provide the required input file, and the system will handle the conversion, simulation, and visualization process. We also test the model under different traffic scenarios to evaluate its performance.
Moving on to our solution, we have developed an automated we have we have developed an automated data preparation workflow to streamline the process. The workflow consists of 7 main steps. We begin with configuration and initialize, where a single config.json file drives the entire process. The first step is network acquisition. Second step is land use extraction. The third step is data refinement. The fourth step is agent upsampling, where we use the data final trips.csv from activity sim as the main input for expanding the agent. Then the fifth step is MATSIM plan generation. The sixth step is network processing. And the seventh step is simulation execution. I will go into the detail of each one next. First step, network acquisition. We use Overpass API to get Bangkok road data from OpenStreetMap. Then a Python script filters the area and road types, and the output is a clean OSM file ready for MATSIM. Next, land use extraction. We use OSM-NX to collect facility data from OpenStreetMap. Then we classify it into activity types like schools, restaurants, and parks. And the output is a structured CSV file for agent activity assignment. Next, in step 3, we clean facility names, classify OSM text into activity types, and map each facility to a subdistrict. And the output is a clean CSV file ready for the next step. The step 4 is agent upsampling. We scale the baseline trips to 300,000 agents and assign real latitude, longitude locations. The system also distributes agents to different locations to reduce artificial clustering. Next is step 5, MATSIM plan generation. We convert the assigned trips into MATSIM XML format. We also apply time jittering, so clone agents do not depart at the exact same time. And the final output is a micro-level plan file with UTM coordinates ready for simulation. Step 6 is network processing. We convert the raw OSM load data into MAXIM nodes and links. Then we clean disconnected loads to ensure continuous routing. And the output is a compressed network.xml.gz file ready for MAXIM. And the last step, simulation execution. MAXIM use three inputs, including config file, load network, and agent plans. It simulates traffic interaction and routing, and the output is event logs and plan for evaluation. This slide shows how our simulation speed up. We switch the simulation engine from QSIM to AMAze to reduce computation time. AMAze use event-driven processing, so it only calculates when traffic events occur, and this reduces simulation time by about 70%, making large-scale Bangkok simulation feasible. This slide shows our new feature, customizable traffic scenarios, which is user can select conditions such as lane, accidents, road closures, or flooding, and then the system automatically adjusts the network parameters such as speed and load capacity. Then we can run the simulation and compare the traffic outcome with the normal condition.
Okay, next, let's look at the outcome and evaluation of our project. First is the software outcome. We developed a GUI to simplify configuration and simulation, which we will demonstrate how to use the GUI in the demo section. It runs it runs locally on a PC. Recommend specs are 8-core CPU with free 22 GB memory. And for a large-scale simulation of 300,000 agents, it takes about 6 hours to complete. Finally, regarding workflow efficiency, we consolidate a complex 7-step process into just 2 main steps, config and run. This automation significantly reduces both time and manual effort. Next is the evaluation. The first aspect is data integrity. The first metric is the agent retention rate. Since our agent data passes through several processes, such as cloning and formatting transformation, we need to check the agent retention rate to determine whether any agents are lost along the pipeline. The results show 100% integrity. No agents were lost, and every agent can be fully tracked back to the original source data. Next is spatial accuracy. We assign facilities to agents and verify if they are placed in the correct TSZ or subdistrict. Out of 300,000 agents, we archive 95% accuracy. The 5% variance mainly occurs at zone boundaries where facility can be overlapping. Our final evaluation is simulation fidelity, measured by the travel time ratio. We compare simulation travel times against Google Maps across 30 origin destination pairs during 3 peak periods, morning, midday, and evening. This validates how closely our model reflects to real-world traffic. Looking at the results, here is an example pair, Chatuchak to Silom. You notice a slight deviation from Google Maps data. For overall 30 pairs, we successfully validate 62 out of 98 routes. Our simulation averaged 22 minutes compared to Google's 26 minutes, meaning our model is slightly faster. This results in a 25% error rate, or a difference of 6.8 minutes.
Next is conclusion and next step. Let's begin with a summary of our achievement, which divide into 4 main points. First, we simplify a complex workflow into user-friendly system control entire to a single GUI file. Second, we build activity sim and man sim, converting Bangkok statistic travel data into daily plan, accurately map on OpenStreetMap. Third, we build a Bangkok traffic handling over 300,000 daily agents, which can be adapted to hard region. And the last, we verify our model accuracy using real travel time from the Google Maps API. From our next step, we will scale to full simulation with 3 million agents running the permit on AWS. Reduce simulation time by 70%, taking about 40 hours. However, to prevent memory issue, we need to disable the rammer. Next, we integrate maximum emission to calculate carbon dioxide and PM 2.5 for future research. Next, let's see demonstration.
Welcome to the demonstration of our project, Automated Activity-Based Travel Simulation Framework for Bangkok using Maxim. To get started, we launch the GUI using a simple Python command. And here is our software. Let's look at the first tab, Input. The initial step is defining the bounding box. To select our area of study, clicking here, an interactive map will be up here, allowing you to draw an boundary for the simulation like this. Okay, next we brought our input files here. You can import 3 files generated from ActivitySim and share file used for statistic segmentation here. And you can adjust the sample size you wish to simulate here. Okay, moving on to the next tab, Execution. This section gives you flexibility to run the entire pipeline or just preparing the data for Maxim. And you can configure your memory allocation here, and you can browse a specific Maxim config file here, but we also have included a default configuration too. A key feature is ability to apply traffic conditions. We provide a guide how to create these condition files for today's demo. Set up 2 scenarios, which are here, which are heavy rain and road maintenance or road repair. You can apply these specific road types or individual network lanes like this. We can adjust 2 primary variables, speed and capacity. For instance, during heavy rain, we reduce both speed and capacity to reflect real-world driving constraints. For road repair, we simply set the capacity of the choosing link to 0. Okay, and the last step is API keys. We use Google Maps API for validate the simulation results against the real-world traffic data. Okay, once everything is set, we just hit run simulation here. And the program will run the pipeline to completion. Once the simulation is done, we will use SimWrapper to visualization our output. You have to go to SimWrapper website and choose your output folder and click events to see the output. And what you see is a full-scale simulation of 300,000 agents traveling across the entire Bangkok. Now let's compare a baseline scenario and a rainy scenario on the right. Visual data clearly shows increased congestion on the right due to the weather conditions. You can also observe the specific links we close. You can see that no agent has here. This is the link that we close. Finally, let's look at the validation results. when we compare 30 rounds to real-world benchmark, the average value, the simulation is about 22 minutes and the real is about 26 minutes with an mean absolute percentage error 25. Okay, let's thank you for watching. And next part will be Q&A section.
Okay, thank you. Professor Fukuda, please.
Okay, so thank you very much for the second team of today's presentation. I also enjoyed your presentation as well, like the case of the first team. But your team, second team, is mainly working on the possible automations of the all of procedures of activity-based model utilization from the data preparation for the executions of simulation by assuming several future policy scenario for traffic congestion mitigation. So your presentation is also very, very comprehensive and very, very promising, I think, and also quite relevant to the our project working with Dr. Vera called 3D traffic project. And yeah, in that sense, your study is also very, very promising. But maybe some clarification question would be given to you. Okay, so firstly, in your simulation, did you consider the differences in household or individual attributes in agent? It looks like that. Your simulation right now is assuming homogeneous agent instead of heterogeneous agent, which may be different in terms of attributes of household or individuals. That is my first question.
Will you answer the question? Or do you understand the question?
Yeah, I understand.
Okay, in your agent simulation, for example, did you consider the difference in household attributes or individual attributes such as age or gender or any other attributes?
Okay, for now, we
Not yet. It's no
not yet,
problem,
but
even if you do not consider.
we
I
only
think,
focus. Sorry,
please.
we only focus on our simulation. Like we focus only activity types and we randomly assign the location.
Okay, I understand. Okay, so in the future work, your team and the former team, maybe your study works would be integrated. For example, the output from the team number one synthetic population may be utilized as an input for the second team MATSIM execution, ABM execution. By doing so, detailed attributes may be considered. Yeah, I expect the integrations of both teams. Okay, so my second question is the speed up in your automation. I am not so familiar with Hermes. So could you please explain more detail about what is Hermes you utilized in your speeding up strategy?
The different between QSIM and AMS is how to count the number of car. The QSIM is uh count the number of car in every second, but AMS is only count the car when the car is move in and move out in on the road. So it not count the car in every second, and it can use less memory, so we can run the simulation by the time is reduced by 70%. But the MS has some limitation is about is it has uh it mm, uh, it 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 also has replanning as QSIM, but it's not good as QSIM.
QSIM is better because they count at every single of time unit. But
Okay, thank you.
it's much slower than MS.
Okay, thank you very much. Okay, I may move on to the next question. So you validated your simulation outputs from some aspects. Can I see slide number 21, please? Yes, here you mentioned integrity. Could you explain more detail about the concept of data integrity? I am not so sure about this concept.
Because the agent's data has passed through many processes of in the pipeline. So we have to check that the agent's data is still the same from the original source.
Sorry, but original data, now you are comparing original data and final output?
Yes, yes.
Okay. So, and you confirm data set are completely the same.
Yes, from we compare the agent from the original data which from activity sim and compare with the output from the pre-processing step, and the agent still the same 100%.
Okay. I roughly understand what integrity means. Okay, and can I see the next slide? Slide 22. Okay, so this is a validation result of spatial accuracy. And okay, the result looks very nice in terms of spatial accuracy rate. But in your simulation, what about the size of traffic analysis zone? Is it city scale or street scale or region scale? What is the average areal size of TAZ in your analysis?
Is a sub-district of Bangkok.
District level.
Sub-district.
So do you think it is well highly resoluted?
Sorry. Can you repeat that again?
Okay, you say district level, but I cannot imagine how big the district is. But is it suitable for example, some detailed analysis considering the spatial differences?
Can you show the map of the
Mm.
sub-districts of the
Ah,
tier?
yes.
Not sure.
Is it not in the slide?
Not sure.
Not in the slide. Oh, we have.
Ah,
Okay.
Okay.
So how I briefly understood. Okay, I think that is maybe transportation planning strategic zone utilized in Bangkok. Okay, so I understand. Okay, so anyway, the accuracy, spatial accuracy is very, very nice. Okay, my last question is about uh, the use of Google Map for comparing the travel time from one origin to one destination. I think slide number 20, yeah, 4 or 3, yeah, this one. Okay, so in order to compare, you have to specify which particular day are you going to use Google Map. The result will be fully dependent on the choice of the date in which you will be getting the data from Google Map. How did you determine the day?
We use data of Tuesday.
Tuesday. Why Tuesday?
Is the next Tuesday is a algorithm of Google Maps. We choose one day and we query for next Tuesday.
Hmm.
so
Um,
why Tuesday?
Why not, for example, why Tuesday, not Monday or Wednesday or Friday?
I think it's normal working day, so I choose Tuesday.
No more working day.
Yes.
Tuesday is a typical day where you observe typical traffic pattern in Bangkok. Do you believe?
Um, 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 Sorry for this question. We're not sure that
Mm,
we should use the Tuesday for observation, for uh, evaluation. We
mm,
just use
Any day.
the same time, the same day that we evaluation
mm,
with the exactly time.
mm.
Uh,
Okay.
we test, we evaluate this metric on Tuesday, so we just use that day.
Okay, thank you very much. And okay, so my last question is your proposed simulation applicable to other some transportation demand management measure? For example, the introductions of congestion pricing in the city center. Is it possible to evaluate such transport policy by using your methodology?
Can you repeat again, please?
Okay, my question is the applicability of your simulation for other transportation policy, such as congestion charging or congestion pricing policy. Is your framework applicable to evaluate congestion pricing policy in the future?
อืมอืม
Do you understand the question?
Yes, yes.
Okay.
I think we can measure the congestions in specific zone, which zone is congest. I think we can apply to that policy.
Yeah, I think in order to evaluate congestion pricing, in your activity-based model, MATSIM, you have to accommodate the impact of price congestion charging in the utility function. If charge is introduced, agent may change their activity pattern. So such kind of thing should be incorporated. Yeah.
Okay.
Then you can do the policy analysis of congestion pricing. Thank you very much.
Yes, but we have to do with QSIM, not Hermes.
Okay. Okay, that's all of my comments for group number 2. Thank you very much. I enjoyed a lot.
Thank you for your question and recommendation.
Thank you very much, Professor Fukuda, for your comment and your participation in this evaluation. And I think please fill in the evaluation forms that I sent you with the email too.
Yeah.
Thank you very much indeed.
Okay, thank you very much, Dr. Vera and your students. And I think both of your study output from 2 teams would be very, very relevant and promising. And as I mentioned, the project for first project and second project are interrelated with each other and also relevant to the 3D traffic project. So, Dr. Vera, for example, is it possible to maybe enhance the both of study teams' works, which may be further enhanced by which can be contributing to the working group number 2. I would highly expect such kind of evolutions of the study output. And also another possibility would be maybe these 2 projects, for example, can be, for example, shared by using, GitHub with the credit for the developers of each team. So, Dr. Vera, please consider such kind of extensions.
Yes, we actually considered integrating the both work together into one pipeline, and also about the code sharing on GitHub is also in our consideration too.
Okay, thank you very much.
Yes. Okay, thank you very much for today. Let's end the meeting.
Okay, thank you very much, everyone.
Bye-bye.
Thank you.
Bye.
Thank you.
Okay, thank you very much.